Hello, everyone, and welcome to today's session on near-surface turbulence. As usual, we're having two speakers. Each of them will talk for 25 minutes, and at the end, we'll have the question session. And our first speaker for today is Dan. Dan got his PhD from Princeton University and is currently a postdoctoral researcher at ETH Zurich in the Institute of Fluid Dynamics, and his work focuses on motor phase turbulent flow. With that, I'll stop sharing and hand it over to Dan.
Looking at ways to extract the wave features from velocity data alone. But in this work, we're going to be looking at ways to infer a statistical relationship between the velocity that we measure and the surface elevation, because that's kind of working with the data that we're able to take in the lab. So once we do this triple decomposition and we've analyzed or identified the turbulent part of the velocity, we can ask what characteristics it has. And one starting point is this theoretical work from Teixeira and Belcher, where they're looking at waves that are interacting with the pre-existing turbulent flow. So this doesn't have any effects of like wind shear or things like that. But one result here is that as the waves are passing over the turbulence, we're going to be periodically stretching and compressing the turbulent structures in a way that's going to increase the streamwise turbulent Reynolds stresses under the wave crests. So we want to see if these effects are visible in the data that we take. So I'm going to be showing results from two data sets today. The first is an experimental data set where we have wind-driven waves, which we measure in the lab. These experimental measurements consist of velocity and surface deformation fields that we take with particle image velocimetry and laser-induced fluorescence. Then along with that, we're going to be looking at synthetic data. So this is data that we build up numerically, trying to match certain aspects of the experimental data set. But this is going to give us a ground truth that we can compare the results of our analysis pipeline with to see how well it matches what we're imposing in the synthetic data. So the experiments are performed in this wind-water-wave tank that we have here at ETH. So air is blown from the left to the right, and it induces waves in the water and turbulence underwater. Then we make measurements at the downstream end, including particle image velocimetry and laser-induced fluorescence. This is just a slow-mo movie of what the waves look like. So the pitot probe, we characterize the velocity profile, and we get a wavelength of around 23 centimeters for the peak wavelength. And then most importantly, with the particle image velocimetry, we resolve velocity fields over about 2 wavelengths. So along with that, we're going to be looking at synthetic data. And as I mentioned, this is giving us a ground truth that we can compare our statistical results against. So we build up the synthetic data by first taking a linear shear profile, then adding onto it an orbital velocity field that we calculate by first taking the same experimentally measured wave profiles that we have from the experiment, and then just using linear wave theory to say what the orbital velocity might be underneath. And then finally, we're adding on top of that some spatially correlated Gaussian noise, which is representing turbulence. And so these three fields together are comprising this synthetic velocity field. And the idea here is that we can take this single synthetic velocity field, pass it through the same analysis pipeline that we have, so it's performing the same triple decomposition. And then we're going to see how well we reproduce the features that we imposed in the mean flow, the orbital flow, and the turbulent flow. All right, so this slide is an animation showing the two data sets. So the experimental results are in the left. We're looking at the horizontal velocity with the wind blowing from the left to the right, and you can see the waves are moving and inducing some orbital motions, but also with turbulence on top of that. Then with the synthetic field, we have the same profiles, which were first imposing this linear shear profile beneath the mean flow. Then on top of that, we're adding, as I mentioned, the Airy wave solution for the orbital velocities, given these surface profiles. And then finally, on top of that, the spatially correlated Gaussian noise, which is representing the turbulence. Then with both these data sets, we can take the results that we have in this rectangular laboratory frame and do a transformation that gives us results in a surface-aligned frame. So here, the psi coordinate is going to be parallel to the surface when we're at the surface. And this zeta coordinate is going to be normal to the surface. And then the farther you get from the surface, it's going to be relaxing to the laboratory Cartesian frame. All right, so we can start by looking at the first of the three components of the triple decomposition, which is getting the mean velocity profile. So working first with the synthetic data, I've plotted with the black line the imposed shear profile that we have in the synthetic data. So the vertical coordinate is the depth beneath the mean water level, and then the horizontal coordinate here is the mean velocity. And the first technique that we can use to perform this average is just to kind of parameterize our results by the distance beneath the mean water level, which is c equals 0. And then we're saying for all the instances where we have water present at that depth, we're going to average the velocities over that depth. And we see that when we get above the point that's coinciding with the lowest wave troughs, this average starts to increase because we're preferentially sampling the forward orbital motions that tend to happen when you're above the wave troughs. So this is not giving us an especially meaningful mean velocity profile. And the next thing to consider is looking at points that are now parameterized in the surface-aligned system. So now instead of z, we're going to be looking at things as a function of zeta, which again is the distance beneath the instantaneous surface position. And then if we do an average where we take values along this line of constant zeta, but space the points equally in the lab horizontal frame, we get this curve, which is still increasing a bit relative to what we've imposed. And the reason for this is that we're kind of capturing the Lagrangian transport that's associated with the wave. Because when points are at a given distance beneath the surface, they're moving with the surface and feeling the same Lagrangian transport that fluid tracers are. And it turns out a nice way to get around this is to instead average things over the transformed horizontal direction psi here. So now we're still taking data that's along some line of constant zeta, but instead spacing the points equally in the psi direction. And the result here is that we're going to have loosely packed points when put back into the lab frame under the wave crests, and densely packed points in the wave troughs. And this is going to bias us towards the negative orbital velocities during the troughs. And this cancels out the Lagrangian drift. This is associated with us being attached to the surface, and lets us recover the mean profile that we're expecting. So we can do the same kind of averaging on our experimental data, and we get the mean velocity profile that's shown here. So again, we get the depth on the y-axis, and here it's normalized by the peak wavelength, and the mean velocity on the x-axis. So this is the first of the three components of the triple decomposition. And now the next step is going to be to decompose the remaining fluctuations into the orbital and turbulent components. And we've looked at three methods for doing that. So the first is using linear wave theory, where we have the snapshots of the water surface elevation. And we can assume that every mode we see here is going to be propagating to the right at a speed that's given by the linear dispersion relation. And once we can do that, we can just analytically find the subsurface flow, which satisfies this boundary condition. The second approach that we've used is the spectral coherence method, which is described in this paper from Zippel et al. And the idea here is that we're going to spectrally correlate the surface elevations to the velocities at some depth beneath the surface. And then we're going to recover what part of this velocity is coherent with the surface and call that the orbital velocity. And the final method, which is the one that we're going to end up using for the rest of our analysis, is this phase-locked averaging approach, where for every point on the wave, we can assign using a Hilbert transform, the wave phase phi and an amplitude a. And then we're going to say for a given depth beneath the surface, what's the average velocity at that depth? conditioned on the overhead wave having some wave phase phi and amplitude A. So go into a little bit more depth on how this phase locked averaging is done. So here's one snapshot of the surface elevation. The amplitude that we get from the Hilbert transform is going to envelope this signal. And you can see that it's not quite constant over the course of the snapshot, and it's varying, it turns out much more over the course of the entire data set. And the wave phase that we assign is going between negative pi and pi, with it being 0 at the wave crests, and then negative pi or pi at the wave troughs. And these are just illustrations of the two components of the orbital velocity that we get, which are, pretty much in agreement with what you'd have from linear theory, where with the horizontal velocity, it's moving in the direction of the wave when you're under the wave crests, and it's moving back upstream when you're under the wave troughs. And yeah, similar picture with the vertical orbital velocity. So I mentioned that
we lost audio.
No.
I can hear.
I can hear.
I can hear as well.
I can hear as well.
Okay, great. So the phase locked averaging, I mentioned that we're fitting results by amplitude as well as the wave phase. And it turns out that that's quite important for the conditions that we have. So here we have, as a function of the wave amplitude that we get from the Hilbert transform, the magnitude of the orbital velocity at 1 centimeter beneath the surface. You can see there's pretty much a linear trend with the orbital velocity magnitude and the wave amplitude. And had we not considered the wave amplitude when we're doing this decomposition, we'd be assigning a singular orbital velocity amplitude to all the points at this depth beneath the surface, regardless of the wave amplitude. And this would lead us to, when the wave is big, there would physically be a large orbital velocity, but we'd only characterize or classify some of it as normal orbital velocity, and the remainder would be called turbulence erroneously. And the same thing would happen with like abnormally small waves. So including this amplitude binning is essential to getting like an accurate decomposition between the orbital motions and the waves, particularly when the wave field you have doesn't have a singular amplitude. And here's the same results with just different depths beneath the surface. So you can see there's pretty much always a linear trend between the amplitude and the orbital velocity magnitude, with the slope decreasing with depth. All right, so we can compare first how this phase locked averaging compares with the spectral coherence by looking at how well it recovers the synthetic orbital velocities that we impose. So again, with the synthetic data, we know what the quote unquote true orbital velocity should be. So we can look at the mean difference between what we recover with the method and the imposed ground truth. And we see that both methods perform pretty similarly. And we can do a similar analysis with the experimental data. And the difference here is that we don't have a ground truth where we don't know for sure what the orbital velocity is. But we can instead look at like how much of the total fluctuations UX are being described by the orbital velocity that we come up with. We get very similar results for both the phase locked averaging and spectral coherence methods. And linear wave theory is performing not quite as well, but also in the same ballpark. So in the end, we're going to go with phase locked averaging to define our orbital velocities. And that's because, for one, it's more suitable for experiments where you don't have a large field of view. So one drawback with the spectral coherence method is that in order to uncover some coupling between the velocity and the surface elevation at a given scale, both fields have to be resolved at that scale, which is not the case with phase locked averaging. Another benefit here is that we're not imposing a linear relationship between the orbital velocity and the surface elevation. But a drawback is that it's not going to capture the orbital motions that are induced by smaller scale waves. This is because with the Hilbert transform, we're getting a single value of phi and a single amplitude that we're assigning to a point. So it's really looking at kind of just the most prominent wave mode. But having done that, we can now perform the triple decomposition, where we're taking the total flow, which is shown on the left here, decomposing it into a mean flow, which is varying just in depth, orbital motions, which are again coherent with the waves, and finally the turbulence, which is the leftover part. And to do some physical analysis here, we can start by considering the structure of the flow along this surface parallel direction. So specifically what we want to look at first is how correlated the flow is with itself between 2 points that are along this line, which is like some fixed different distance beneath the surface. But then because we've done this triple decomposition, we can consider the orbital and the turbulent parts independently and see how both are contributing to the overall correlation. So plotted in black, the autocorrelation along this line, which is 1 centimeter beneath the surface. The separation distance along this surface parallel direction is on the x-axis, and the correlation is on the y-axis. So you can see, as you'd expect, at very small correlations, the flow is small separations, the flow is highly correlated with itself. But then as you get farther away, the correlation decreases. But then you get this oscillatory behavior, which you might expect is coming from the periodic nature of the orbital motions. And we find that that is in fact the case. So when we look at the autocorrelation of just the orbital part by itself, we get this oscillation that's peaking again 1 wavelength away from the starting point. But then I think more interestingly, we can look at the autocorrelation of just the turbulent signal, and we get this monotonically decreasing function here, which is telling us that kind of is like the case when you have a turbulent flow without waves, the turbulence is eventually becoming decorrelated with itself as you get to bigger and bigger spatial scales. So what we can do with this is we can do an exponential fit to this autocorrelation, and this is going to give us an integral length scale for this depth. So I'm showing that on this snapshot here, where the background is showing us the instantaneous horizontal velocity. And you can see by eye that near the surface, the spatial scale of the coherent velocity structures are smaller than they are farther away from the surface. And this is reflected in the fact that the integral scale is growing the farther you get from the surface, and it's approaching, in this case at least, about 1 wavelength. And we can do the same thing now with the vertical velocity fluctuations. And you can first see by eye that the scale of these, the spatial scale of these fluctuations is decreased relative to what we had with the horizontal velocity. And this is again reflected in the integral scale that's based on these vertical velocity fluctuations, which is smaller than what we have for the streamlined velocity, and is also growing as we get away from the surface. So we can compare these length scales now to what we have, or to the length scales of the waves. So this plot is showing us a length scale that's normalized by the peak wavelength. And to start, we can look at the distributions of all the wavelengths that we measure with the Hilbert transform. And we get something that's somewhat broad, but still peaked around, of course, the peak wavelength. Down here is the gravity capillary scale. Then the 2 wavelengths, or the 2 integral scales that I just showed, are these 2 curves here. And we can do a comparison to the integral scales that we would have for the turbulent boundary layer that exists under a flat plate. So this is taking numerical data from the simulation from Solero et al. So this is a flow that doesn't have any waves, and it's just a turbulent flow over a flat plate, which mimics our flow in certain ways. So we see that the farther we are from the surface, we approach an anisotropy, which would be like the ratio of these 2 length scales, which is similar to the case with a flat wall. And then in both cases, the length scales are decreasing as you get close to the surface. And then finally, as like a lower bound for the spatial scale of the turbulence, we can calculate the Kolmogorov length scale once we have an estimate for the dissipation rate, which I won't talk about for the sake of time. But you can see this is much, much smaller than the waves. So this plot is telling us overall that the turbulent motions, which are spanning from this Kolmogorov scale all the way up to the integral scale, are much smaller than or up to approximately the same size as the wave scale. And we can also look at now the structure of the flow by considering the typical velocity difference between 2 points along this line. And this is going to be parameterized by the second order structure function, d2. So it's telling us for some spatial separation, what the typical difference in velocity squared between 2 points at that separation is going to be. And again, with the decomposition, we can consider the contribution from the orbital flow and the turbulent flow separately. And we can do some Taylor series expansion to expect that this orbital second order structure function is going to scale with the separation to the power 2. And a canonical result from turbulence is that in a turbulent flow, it's going to scale with the separation to the 2/3 power. So we want to see if this 2/3 scaling also holds in the wavy flows like we have here. All right, so in black, I'm showing this second order structure function for the entire flow. So before doing the decomposition, the separation scale is on the x-axis, and the typical squared velocity difference is on the y-axis. So we get, again, this oscillatory behavior in the overall flow. And we see that this the oscillations are coming from just the wave part again. And at small separations, we indeed get this separation squared scaling, which we expected. And along with that, we get the same 2/3 scaling that we have in more canonical turbulent flows. And this is related to this point that was made at WISE in earlier this year in Seattle. So this is a figure from a paper from Ziemann and Thompson, which was presented. And this was looking at field data, where if you have a measurement of the velocity beneath the surface in the field, you can do a similar procedure to extract the dissipation rate. And here they're showing that if you're to do that based on the overall flow without filtering out the waves, you get this kind of erroneously large value of dissipation that goes with depth -2. And only once you filter out the waves and consider the turbulence by itself, do you get this z to the -1 scaling in the dissipation. Yeah, so our results are also showing that this triple decomposition is a critical step in extracting the dissipation rate. All right, and to finish, I'm going to talk about how the turbulent structure might vary over the course of a wave. So again, we're going to be looking at spatial separations along this line that's some distance from the surface. You can see as the flow is moving, the physical length of this line, when put back into lab space, is changing. And it's going to depend on whether we're underneath a wave crest or a wave trough on how long this line physically is. So in order to do a fair comparison between the structure between the flow under crests and that under troughs, we're going to parameterize the distance now by this delta x rather than delta psi. All right, so if we start by considering the second order structure function that one gets, solely considering separations that start under wave crests, we get the curve that's shown in blue here. You can see that the turbulence under the crests, at least at small scales, is more intense than what we have overall on average, which is the dashed line. And similarly, if you condition your second order structure function on starting just under the troughs, you get the result shown in pink here, where it's less intense than overall. So this is telling us that the small scale turbulent features are more energetic under crests and less so under troughs. And this is just the same data but now shown as the ratio between the conditional second order structure function and the overall one. So we're seeing that at small separations, there's going to be 20% difference between the mean and what you'd have under a crest or under a trough. But we want to check how sensitive this result is to the fact that we might be mischaracterizing some orbital motions as turbulence because we're not properly decomposing the turbulence from the waves. So what we can do is we can go back to the synthetic data that I showed initially, where we know that there should be no difference between the crests and the troughs, and see how much of an artifact is induced by our analysis. And that's what's shown in this line here. So we see that we are missing some turbulent motions, we're missing some orbital motions that we end up calling turbulence, which is contributing a bit here, but it's smaller in magnitude than the effect that we see experimentally. So this is leading us to believe that this is a physical effect that's like telling us about the nature of the flow under crests versus under troughs. So just to end, we can think about why physically it might be the case that the turbulence is more intense under the crests. So I showed this picture at the beginning of the talk. It's results of theoretical work that says when waves are interacting with turbulence, you're going to end up with more intense turbulence under the wave crests. But also, in our case, we have an airflow over the surface. This is a figure from the paper from Kianoosh, who's going to talk next. But it's showing that the shear stress that the wind is exerting on the water tends to be maximum just under the wave crests. So we think this is also an explanation for why the turbulence underneath the surface is more intense here. So I think for the sake of time, I'm going to leave the takeaways on the screen here, but thanks for your attention, and I'm happy to take any questions.
Thanks, Dan, for the nice talk. I think for the sake of time, we'll just keep the question to the end of the talk, or you could drop them in the chat if you want to ask anything now. With that, we'll move to the second speaker. So for the second talk, we have Dr. Kianoosh from University of Texas at Dallas. Kianoosh got his PhD from the University of Delaware and is currently now the lead of flow dynamics and turbulence at the University of Texas. And his research focuses mostly on turbulent flow, surface gravity waves, and S interaction. With that, I'll hand over to you to give your talk.
Thank you so much, Bernard. Just to check, do you see my screen? Okay, all right, perfect. Thank you so much, Bernard, for your kind introduction, and good morning, everyone. And thank you to the WISE committee, the WISE webinar organizing committee, for inviting me. It's an honor to present that WISE webinar. So this is Kianoosh again at UT Dallas, and today I'll be sharing some of our recent work on modeling turbulent structure using the data-driven, basically the machine learning techniques, which is a combination of, it's my students' work, some of my previous work. So my talk has basically two sections. One, first I'm talking about the skin friction drag, which is that I presented some of that at WISE meeting as well. So I'll go very quickly on that. So the introduction, I'll go brief and quick as well. We all know that RC fluxes are important for sea state and the weather patterns and basically for accurate prediction of extreme weather events. And there is still a lot of work needs to be done, specifically for parameterizing the RC fluxes that has some better understanding about near surface, small scale, basically interactions and processes that happens near the surface of the ocean. So when waves are appearing near the surface or at the surface, basically there is a complex interaction between the mean flow and wave coherent flow and also the turbulent flow. And at the surface, this momentum flux, total momentum flux or wind stress, basically will be a combination of a skin friction drag and form drag. So the total wind stress or the total RC fluxes, momentum fluxes, and energy fluxes inside the wave boundary layer are of high interest to be able to be parameterized. So, but these processes or these fluxes are going to be affected with different sea conditions like wind speed, wave age, wave slope, and wind wave alignment, right, or misalignment, basically. So there are too many parameters there that made the sea state dependent parameterization of RC fluxes quite challenging, and still it's of interest to be able to have those kind of parameterization. So recently, with the data-driven kind of modeling approaches, there have been some improvements in modeling of some of these parameters. So in the literature, there has been use of POD, the proper orthogonal decomposition that can basically capture the most energetic modes, and the dynamic mode decomposition as well that can basically capture the spatial frequency and the time dependency. So the CNN are the convolutional neural networks, and the generative adversarial kind of networks or GANs has also been used for reconstructing near surface flow fields from wave measurements or from a sparse kind of low fidelity measurements as well. And also physics-informed neural networks or PINs has been of interest as well, including like some Fourier neural operators and some physics-informed kind of diffusion models. I don't want to go directly to explaining the literature on that. It's a lot of literature. I just want to mention a couple of techniques that has been used successfully for the purpose of reconstructing the near surface turbulence in the field. So here we are trying to use our experimental data that we have in order to be able to develop some of this parameterization, specifically for near surface turbulence structure and the skin friction drag. And because these are experimental data, there has been a lot of challenges in getting these, but I just want to share first the experimental data set that we have. So the experimental data set is basically the airflow above or turbulent flow above wind-generated waves that we are using for this modeling purpose. And here is a schematic representation of the instrumentation setup. So we are using particle image velocimetry and laser-induced fluorescence techniques. So these are the data, and the papers has been published. I'm not going to the details of these experiments, but I just want to show an example of the wind side or air side kind of flow from the PIV. So here, this is an example of instantaneous horizontal velocity at a wind speed of about 5 meters per second. That's a U10. That's 10 meter extrapolated velocity, basically. And once we have this kind of turbulent velocity or instantaneous velocity, we can extract the turbulence, we can extract the wave age, we can extract the wave profile, and we can also calculate the viscous stress or skin friction drag out of that. So, and these are basically the information that I'm going to use, or we are going to use to develop our models. So I start with the skin friction drag prediction. So the main objective of this skin friction drag prediction is to be able to estimate the instantaneous skin friction from wave profiles and wave ages only. I say wave profile and wave ages, but as an input, I use wave profiles, the local slope and phase, because these can be directly obtained from the wave profile, basically. So my only independent parameters that I need to have is wave age and surface profiles, basically. So, and I use these to approximate a CNN or a mapping, right, using a CNN model that consists of different convolutional, flattened, dense, and nonlinear layers, basically, and it minimizes an L2 norm between the ML predictions and the ground truth experimental measurements. So let's take a look at the experimental input. So here is what we use as an input for this skin friction drag CNN model, basically. So the first column shows a velocity over a non-separating wave, and the second one shows the velocity over a separating wave. So the first row is the horizontal velocity to have the perspective of how these waves are going to look like, and we have the wave profile highlighted with a black line on them. So the second row is basically the local slope. It's basically partial eta, partial x. The third row is the phases. These are the local phases that we can extract using the Hilbert transform that Dan mentioned. And obtain the local instantaneous kind of phase from these waves. And the last row shows the viscous stress or the skin friction drag at the surface, or closest measurements that we have near the surface, which is on average around 90 micrometer to the surface, basically. So we have a different set of experiments. So we use the experimental data set with wind waves only. So our 5 different cases that we have, the wind speed is varying from 2.3 up to 16.6 meter for U10. And again, this is 10 meter extrapolated wind speed. And that would correspond to waves or wind waves with a slope as small as 0.07 up to 0.27. So out of this data set, I'm using 3 experimental cases to train the machine learning model. So I'm using the cases with a wind speed of 5, 9.5, and 16.6 meter per second. So in total, I have around more than 13,000 input-output pairs, and we split the data to 80% training, 10% validation, and 10% testing. So there are 2 other cases that we are not going to touch. We just keep them, we just keep them as is, and we do not use them for training. We get back to them to see how the model can generalize over these unseen cases. So here is the MSE convergence history of the training and validation, basically. So we stop at epoch 150 for this training, basically. the results that we got was really interesting as well. Let's look at some of this visualization that visually can help us to understand how the machine learning can predict this skin friction drag. So here I'm showing an example of those training from the test data for each experimental case that we use for the training. So the first column is basically the wind speed of 5 meter per second, let's say 1 meter per second. The second column is 9.6 meter per second, and the last column is our highest wind speed of 16.6 meter per second. So the first row again shows the horizontal velocity, horizontal PIV velocities are from experiments. The second row shows the experimental skin friction drag, right? So these are coming from experiments. And the third row shows the CNN prediction. And we can see that visually it does a really good job. So it can follow the trend very well. It can basically detect when the viscous stress drops significantly. So that can be an indication of airflow separation. Even for the highest wind speed, it can do a good prediction for us. But if I want to bring up some more error metrics, more accurate error metrics, basically, we can look at L1 norm and an R square. And here is the PDF, the probability density distribution of these error metrics, basically. The first image on the left basically shows the PDF for L1 norm. So, and we see that on average, not on average, but the most probable error that we get out of this model is around 20% for cases with a lower wind speed of 5 and 10, and for the highest wind speed is around 30%. But these are instantaneous. I just want to mention that because there's a huge difference between predicting these instantaneous events and basically the ensemble average events. So on the right also I have the R square PDF, and the R square does much better. So my R square is around 0.9 and 0.96, which is quite good. And the way that I interpret this is that I can predict the trend of the viscous stress or skin friction drag very well, but perhaps not the peak value. So the discrepancy between the peak value are a little larger than how accurately I can follow the trend. And here are the average over the entire data, not the average, basically over the entire data, the distribution that I have. So now I can get back to the two cases that I did not use for the training, right? So I have a case with 2.25 meter per second, and I have a case with 14.82 that I can use for generalizability of the model. So the case with 14.8 meter per second, wind speed 14.8 meter per second is interpolation. So by nature, I expect that it would work better, but the lowest wind speed of 2.25 is an extrapolation, right? There is it's not in the range of the velocity that has been used to train the data. And there is also another distinction for that experimental case, and that is that in that lowest wind speed, we literally do not have any airflow separation. But the other cases are airflow separation is almost dominant. So we have a lot of wave profiles and wave events that we have show airflow separation over the waves. So let's see how the model can generalize over these cases. On the left, I'm showing an example, two examples of the wind speed of 2.25 meter per second. And on the right, I show the two examples of basically the wind speed of 14.85. And for both of them, again, we can follow the trend very well. And it is exciting to see that this extrapolation or out of training kind of distribution for the extrapolated case with a very different feature of the wave characteristic still does a very good job in predicting the trend. So I do the same thing. I'm looking at the PDF, the probability density distribution of this L1 norm and R square. And we will see that, it's slightly, the error for the L1 norm has increased to 25 and 33%. And again, that's expected because these are unseen cases. So, and the R square is still quite acceptable, around 0.9 for both of these cases. And the largest error that I have for this one is around 33% for the lowest wind speed, which is again extrapolation with a very different kind of features, which is quite acceptable. So, and here is the total kind of average over everything, all the data for all the experimental cases that we can see here. So, but as I mentioned, these are instantaneous errors that we see, right? So if I average everything and look at some average parameters like let's say, phase average skin friction on the left here, or the ensemble average skin friction, my prediction are quite accurate. So it's doing really good, and I'm very happy with that. So I can compare this with all the available measurements, not maybe all the, most of the available measurements here as well, and I see a very good kind of agreement with that data as well. So, and then we continue this kind of research and said, why not trying to obtain the turbulent structure, the total, the overall boundary layer over the waves that we can resolve from the wave profiles only. So that's what we try to do basically to obtain the same kind of model for that. And we use the same data set, the same 3 cases that we use for the training for the skin friction drag. But here, because we wanted to train over the entire data, the data set was quite large, so we had to downsample, and that downsampling of the experimental data will cause losing the small scale features of the turbulence. You will see that here we will miss this much of energy spectra. We also had to filter, so there is also a 5% loss here as well. And we can see here as an example of how these downsampling and filtering can affect. But the network is a little more complex because we need more layer, the more features that we need to extract and correlate to the surface profile. So here is our CNN model that we use. So we have a one-dimensional kind of encoder and two-dimensional decoder. And we are using also a residual block here to address the vanishing gradient problem. But once we started to do this kind of training, we soon observed that we have overfit problems. The data set that we had was not enough to be able to learn all the multi-scale structure of the turbulence. So to alleviate that, to mitigate that problem, we basically use a technique that is called k-fold cross-validation. So in this technique, we are using basically 90% of the data for training and 10% for the test. So, and that out of that 90% training, we basically divide the data set into, let's say, k subsets. And during the validation, and during the training, basically, we use one subset, right, for validation, and k minus one subset for the training, and we continue doing that over the entire number of k's that we have. So that helps us to basically reduce the overfit a lot and get a good results on the PDF as well. So if we have a R-square about 0.9, but when we are looking at the data and looking at some features, we see that a smaller scale structure is not there. So we can observe and we can predict the larger scale turbulence, but not really the smaller scale. So we did not stop there, and we had a lot of different kind of trial and errors in order to be able to capture the smaller scale turbulence and also use the high resolution, full resolution kind of the experimental data. So we tried a couple of different ideas, a lot of them failed, and we ended up splitting the turbulent velocities into a larger scale and a smaller scale component. So, and for doing that, we actually use SVD, the singular value decomposition technique, and we define the first 10 modes of our SVD, right, when decomposed with the orthogonal modes that we get out of the SVD for each instantaneous PIV image. We define the first 10 modes as larger scale, or let's call it coherent kind of turbulence, or dominant turbulence, maybe it's better to call it. So from mode 10 to 90, to 104, which is around 21% of my energy, we characterize that as a smaller scale turbulence. And this characterization is not random. We basically use a definition of Gaussian turbulence to define our smaller scale turbulence, and being able to separate that from the larger scale. So, I'll show that in the next slide. So, and the remaining of that, we see that we observe that it has a very significant kind of behavior similar to a white noise, and our data is experiments. We expect a lot of kind of noise there as well. So we call around 1.5% of the total energy in our data set as white noise. It's not a pure white noise, but it can be called white noise. And we use that technique actually to denoise it. So there is a good mathematical proof and derivation for that, which is above this kind of presentation that I'm presenting here. On the left, I'm also showing the spectrum here for different modes and different component that we discussed. So I guess it would be more interesting to look at the PDF of these signals, right? So I divided, if I go back here, right, I'm calling that larger scale turbulence with U prime, the smaller scale with U double prime, and the noise with UN. I mean, this is my UN and this is my U double prime. So if I go back and look at my spectrum and the PDF of these velocities, I can see that the combination of my U prime and U double prime, the larger scale and the smaller scale, it fits very nicely to my total turbulence that I have. So it checks that out. And the U prime, which is my larger scale, also follows a very similar kind of PDF shape that I have here. But more interestingly is that the area of between 10 to 104 modes that I define as a smaller scale turbulence, I can also call that Gaussian turbulence, right? Because it follows very closely with the Gaussian distribution of a turbulence. So, and that's why we call this as a smaller scale turbulence and separate that from the dominant turbulence. And the line here that you see, it's our noise basically, and that's a white noise that we are using here, and it basically shows very, very accurate, it's not exact, but very accurate kind of behavior for a white noise. And we are very happy with that. So with that, I'm able to basically decompose, first of all, denoise my data, right? So my velocity is now denoise. I take out this noisy stuff out of my instantaneous velocity. And the instantaneous velocity now can be decomposed into the mean, wave coherent part, and also a turbulence, similar to what Dan mentioned. But for my turbulence, I would be able to now decompose my velocity into a larger scale dominant turbulence and a smaller scale turbulence. So that will give me a quadruple kind of decomposition, that I can decompose my instantaneous velocity into a mean, wave coherent, dominant turbulence, and a smaller scale turbulence. And now I'm going to train each of these components separately. I'm using basically the same kind of network that I showed. We have some improvement for that. And the main thing that we added here is that we are using a physics-informed CNN. And by that, I mean that we added a loss function, a physical loss function that is based on the Fourier, the spectra basically. And we are trying to not only minimize the loss in the data, but also in the physical quantity that we are using. So we are basically using different weight for this loss function. So for the mean and wave coherent, these are more average, so these are well behaved, so we can't just use the CNN. So that's a pure CNN model that we are using. But for the turbulence, the large and the smaller scale turbulence, we use a different kind of weight, I guess 0.3, if I'm not mistaken, for our turbulence in order to be able to capture them. So here is the convergence history of my training again, and here is an example of the wave-induced velocities, 3 different kind of examples. And as you see, or kind of expected as well, these are very accurately predicted by the model. So on the first column, you see the ground truth experimental data. The second column shows basically the predicted one, and the last column shows the L1 norm. So it's around less than 0.5% of error. That's fantastic. But now let's go look at the turbulence. The turbulence, the error will increase definitely because it's expected. So by that turbulence, this is my U prime. This is my larger scale. This is the dominant turbulence that I want to predict. And here is, on average, we have around, let's say, 15% kind of error, which is quite acceptable considering the complexity of this data set that we have. Again, the first column shows the ground truth experimental data. The second column shows basically my dominant turbulence. And if I put everything together, I can predict the instantaneous velocity just using the wave profile. And that's it. So just give me the wave profile. I can predict the turbulence structure of the wave quite accurately, around 15%. And here is basically the PDF of my error of L1 norm, basically, that again I have around 15%. That's the most probable error that I observe in my model, basically, for instantaneous cases. So, but again, these are basically instantaneous events, right? So very, very challenging to be able to accurately predict them. And if I average them, here is the mean velocity in kind of regular coordinates and wall coordinates here. We can see that very accurately we can predict the mean velocity out of that. And that is great news. This is remarkable because if we just use the wave profile in order to get these characteristics from the model. So this can act as a very nice surrogate model for any larger scale kind of model numerical simulation that we are using. So this study is we are still trying to finalize some of the details for our smaller scale turbulence, and hopefully we will soon submit the paper out of this. So with that, I guess I can stop with the summary, but definitely have to thank all of my collaborators and students. This work was mainly done with or by my students, and I have to thank all of them for their help and being attentive and doing a great work. So thank you so much, and I'll get any questions that you have.
Thank
So
you,
let's
Yousefi,
stop
for the
sharing.
nice thought. Yeah, so we have only 5 minutes, and Dan, you have like 2 questions in the chat. Do you want to take one? And if anyone has any question, you could raise your hand or unmute yourself.
Sure. I guess I can take Andrew's first question here, and asking about the surface following coordinate system. Yes, I went kind of quickly through that slide, but I'll share the method that we're using. But yeah, so we're starting with data defined in this like laboratory rectangular XC coordinate system. And then based on a Fourier transform that we do with each like individual snapshot of the surface elevation, we get these Fourier coefficients, and each is causing like the transform system to be slightly displaced from the original one in such a way that at the surface, this psi direction is parallel to the surface and zeta is normal to the surface. And then the effect of each mode is decaying back to the Cartesian coordinate system over a length scale that's dependent on like the mode itself. Yes, this is the same method that was used for looking at the flow above the waves in this paper from Buckley and Braun. So if that answers the question.
Yeah, that makes sense. Thank you.
Sure.
Great. Chen, I think you have your hand raised.
Yeah, I have one question for each. So I think I'll start with Daniel. So I'm not wondering, because you have a very controlled environment of experiments, are you able to just repeat your experiments many times to get an ensemble average of your velocity, and then the rest will be your turbulence? I think that's how turbulence is defined. I don't know whether you are able to do that, or that's just simply too expensive.
Yeah, so the videos that I was showing was actually it's like a shorter data set that we took just for the purpose of visualization, but the statistics are based on like 2,000 snapshots, which are like roughly uncorrelated with each other. So over those 2,000 snapshots, we have like a long enough time that we can have a converged mean flow, and then there's also enough information there that the fluctuations we can decompose into the turbulent part and the orbital part.
Oh, okay. Okay. And another question is for Kianoosh. So that is a very interesting machine technique. Thank you for your talk. But I'm wondering whether you can use the same technique to predict surface pressure. I think I'm asking because it seems to me that the surface pressure is very sensitive to different wind wave regime, and if you are only using a subset of the regime to train the technique, whether you are able to use that and predict like the pressure profile at other wave regime.
Yeah, thanks for the question. That's a perfect question actually, and I guess that's a natural next step. But we haven't tried that yet. We do not have reliable pressure, so we can detect. We can apply some numerical kind of calculation on our experimental data to get the pressure, but we have not yet tried that to train the model. from my experience, yes, we can do. How successful it's going to be, I don't know because I haven't tried that, but I expect that we should be able to get a kind of reliable model out of that, depending on a wide range availability of the pressure data over different kind of conditions, sea state condition, let's say. If we have such a data, we probably can develop such a model as well. And that is very interesting. I'm looking into doing that actually.
Great. Thank you. Thank you both.
Yes.
Great, Ryan.
Ryan.
I have a question for Daniel. Thank you for the talk. I quite enjoyed the careful analysis. So when you showed a video of your water surface, I can see quite a bit of 3D structure, right? So like the crest is kind of not aligned all the way across the tank. So what do you think the effect of those 3D structures would be on your analysis?
Yeah, it's a really good question. Yeah, so with this data set, we're just looking at 2D PIV, where we only know the two components of the velocity, like in a single plane. We've done some separate measurements of, like with stereo PIV. So there, within one plane, we're getting 3 components of the velocity. And separately, we've done like kind of 3-dimensional reconstructions of the surface elevation. And we see that most of the energy in waves is moving in the like predominant direction, but there's definitely some, yeah, like it's not completely like 2-dimensional. I think we found that like the length scale over which like the orbital velocity would work out in a single plane kind of works in a different plane in the spanwise direction. It might be on the order of like, you know, like very roughly like 5 or 10 centimeters, but I think it's definitely not like a single orbital flow over the entire span of the experiment. Yeah, so I think the like additional orbital velocities that are induced by those spanwise motions, we're probably erroneously calling them turbulence in a way that, you know, if we had a full 3D reconstruction, we wouldn't necessarily have to. That's a good question. Thanks.
Great. With that, I think we're out of time. I'll ask us to give our presenters virtual claps. And then we'll end the session.
Thank you, everyone. All right. Thanks for that. Anything
Thanks
from
so
us?
much for the talk. Yeah, I think this was great.
All
I
right.
had a little question about like using CNN versus like using transformer, vision transformer. So like, do you think if we use, say, the vision transformer, which I mean take into consideration the global full picture of the image, whereas the CNS, you just have the local within the window. Do you think that will improve the model or no?
Yeah, that's a great question, and I really want to try that one, but I haven't yet, and I believe it does, and I think it does help a lot. But I'm not sure if like for doing that, we probably need a data set that is more. So our data set, it's not consecutive in time. So we have some bad frame that we need to take out. And I believe maybe the data set that currently we have is not the best to apply that time dependency kind of information that is needed for a better model development. Is not capable of doing that. So we are trying to get a new data set that is consecutive over time, and we do not have any bad frame on that. And hopefully with that data set, we can try some transformer kind of techniques, which I believe it does, because one of the drawbacks of this CNN that you saw and the challenges that we have that we don't have any time history of the flow, right? So the model does not have any information about the previous structure that might actually is transferred and evolved over time to the new frame that we are doing this kind of CNN on that. So and
Yeah.
that is missing. So
Cool.
short, my long answer to your question is yes, or my short long answer is yes. Yeah.
Yeah, that was great. Both of you had like very nice graphics, which was very helpful
Thank
in
you.
understanding the information.
Yeah, absolutely. Thank you.
Yeah. All right. Thanks so
All right.
much.
Thank you,
We'll be in
Dan.
touch.
It was
Sure,
nice
take care.
presentation as well. Hope I'll see you all at APS.
Yes, I'll be there.
Yeah, fantastic. Yeah, you have a good one.